Okay, so this week we are doing sort of two things. We're talking about numbers of elements and all the different ways you can order or arrange something. And so we've got the concepts, the fundamental counting principle, combinations, and permutations. And so I'm talking about combinations today. And then we're also talking about probability, which a lot of the probability problems, you have to actually find out how many ways you can arrange something before you can then find out the probability of it occurring, if it's asking for like the probability of arranging something a certain way. So we're going to just focus on combinations today because I have a video on like permutations, and so this is kind of like they're very related, very related. So what exactly is a combination? So, and this is the mathematical term combination, because there is the word combination used in English that has a different meaning, a slightly different meaning. So you want to be sure that you're not getting confused between how we use combination of everyday speech and then the actual mathematical word combination. So the number of ways you can arrange n number of items in any order, so order does not matter, is called a combination. It's the mathematical word combination. In daily life, we may say combination and mean ordered or unordered. It could be either one. So a permutation has order and matter. So a combination is different in that order does not matter. So everyday word, when we say combination, it could be a permutation or a combination mathematically, because when we use combination in everyday speech, we're not really speaking about the order. We're just talking about arranging things. But mathematically, there is a difference between doing it ordered and doing it unordered. And that's the difference between a permutation and a combination. So combination is that order does not matter when we're looking at the number of ways we can arrange something. So picking something first is considered the same as picking it second. If you're picking 5 cards, whether you pick up a king first versus second doesn't really matter when you're looking at a combination. And because the order doesn't matter, there's actually fewer combinations than there are permutations. Because once you start looking at order, then you can start rearranging things and getting more options. Now, like permutations, combinations, you can't pick the same item twice. So if I'm picking from a deck of cards, I'm not putting that thing back in and picking it again. So once you've picked it, it doesn't get picked again. So that's a similarity between combinations and permutations. So the key difference between them is that permutation order matters, combination order does not matter. So when you're trying to decide whether a problem is asking for a permutation or a combination, you have to ask about order. Does order matter? Because that is the distinguishing characteristic between the two. So our formula for the number of combinations of a subset of a group is very similar to the permutation formula. We just have one difference. So you have n things you can choose from, and you're only picking some of them. So that's R. And it's basically the number of permutations divided by the factorial of R. So that's how you're getting a smaller amount. So we're dividing out the number of ways that we can pick some of them. So the formula is very similar to permutation formula, where you've got n factorial over n minus r factorial. But then the difference with combination is then you're also dividing it by r factorial. So they're very similar formulas. So you want to be careful that when you're doing problems that you're doing the correct thing. You're doing a combination when it should be a permutation. And you want to make sure you're using the correct formula because the formulas are so similar. If you're wondering how I was able to type these out, I sent out an announcement yesterday showing how you can type out the formulas because there's not like an innate way to do this in any math typing thing, like in Blackboard typing math, or in in Word when you're trying to type math. There's not really a way to do it easily. So I do recommend that you just handwrite your work, because then you don't have to kind of mess around with how you properly type this so that it's formatted correctly. But if you do want to type it, I did send out that announcement with kind of how you can make it work. So first example, and I've just reiterated the formula here so that way you have that in front of you. So we've got two different examples kind of here. These are small examples. So the first one, to conduct an experiment, researchers randomly select 6 students from a class of 30. How many different groups of 6 students are possible? So this is unordered, meaning combination, because the order that you're picking these 6 students doesn't matter for you to conduct the experiment. It's not going to matter whether someone was picked first versus second. All you need are 6 students. So order doesn't matter, which makes it a combination. So the total number of choices you have is n. So we're picking from a class of 30. So n is equal to 30. Then R is how many you're picking. So we're taking 6 students, so R is equal to 6. So to actually do this formula, we have 30 choose is what I usually use for the C, 6, just to kind of have something to say out loud, 30C6 or 30 choose 6. And so it's n factorial, so that's going to be, oh, and my pen has decided once more, it just needs to kind of be reset. Okay, 30 factorial divided by 30 minus 6 factorial, and then also divided by 6 factorial. So make sure that everything that's supposed to be in the denominator is in the denominator, that when you're writing this by hand, that you've got your line going all the way across. If you're trying to like type this and you're not using typesetting for math, you do need to have parentheses around the total denominator in order for it to be mathematically correct. Otherwise, you would be indicating that you're actually multiplying by 6 factorial versus dividing. So how you write these things really does matter, and the best way to write it correctly is to do it just by hand. So we have multiple choices what we can do at this point. So we could just stick these numbers on our calculator and do like 30 factorial, which is going to be a really big number. Then 30 minus 6 is 24, so that'd be 24 factorial, and then 6 factorial. So we can do these as long as you have your factorial button on your calculator. For small numbers like this, I actually suggest trying to make it smaller first by canceling things out. So what this means is, so we've got 30 factorial on top, and the 30 minus 6 is 24 factorial. So I'm going to just simplify that. And the way that factorials work is you've got 30 on top, that's 30 times 29 times 28 times 27, so on. And then you've got the 24 factorial in the denominator. So at some point, you're going to be able to cancel out the 24 factorial, because you're going to have 24 times 23 times 22 and so on top. So those will cancel out. So this would be 30 times 29 times 28 times 27 times 26 times 25, because the rest of it will cancel out with the 24 factorial. And then 6 times 5 times 4 times 3 times 2 times 1, the 6 factorial. So we can start canceling things out here to deal with smaller numbers. So like I can divide 5 and 25. Actually, 6 times 5 here is 30. So I can just cancel out the 30 with the 6 times 5. Then let's see, 4 and 28, I can cancel those out, and that gives me a 7 there. 3 goes into 27, and that leaves you a 9. And then 26 divided by 2, that gives you a 13. So you can narrow this down and kind of cancel things out so you have smaller numbers to work with, and you don't have to worry about like having this big giant number in your calculator, because depending on your calculator, you may not be able to have every single number. Like, you know, it may not be able to do it depending on how many numbers your calculator can show. So sometimes it's helpful to actually, you know, start canceling things out. Like, for example, on my calculator, if I do 30 factorial, it starts giving me scientific notation. Like, it's just too big for my calculator to do it. So that's why, you know, I want to actually kind of simplify these things first. So we basically canceled out everything. So we just need to multiply the top. So I have 29 times 7 times 9 times 30, and then times 25. And though, so this gives us our answer, 593,775. So that is the number of ways you can select 6 students from a class of 30. Now, it's good to check your work if you have the ability to do a combination on your calculator. So my calculator does have the ability to do 30 C6 in one step. And the way my calculator works is I type in 30, then I go to my probability function where I have NCR, and then you hit 6, and then it will give you the same number. So if you have a calculator that does this calculation for you, you can use that calculation. But what I want to see is still the setup. So if you want to know like how much work you need to show, you need to at least show this step, and this step, where you've kind of simplified it up to like the factorial part, and then you can go to the answer from there. But you do need to show some work, like plugging in so that you're demonstrating that you're understanding the formula and like what the numbers are, and you're not just using your calculator without really knowing what it's doing. So you can use, if your calculator does combinations and permutations, you can use that. Just make sure that you are showing some intermediate steps before you get to your final answer. Are there any questions? Okay, so second example here, we've got a US Senate committee has 10 members. Assuming party affiliation is not a factor in selection, how many different committees are possible from the 100 US senators? So again, if you're just putting people on a committee, the order that they're picked doesn't really matter, because it's not saying that there's going to be certain people that are like the head of committee or anything like that. We're just putting people on a committee. So order doesn't matter. And so this is a combination problem. So N is the total that we have. So we have 100 senators. And then R is how many you're picking. So we're choosing 10 of them to create this committee. So this is 100 C 10. So using our formula, this is going to be 100 factorial over 100 minus 10 factorial times 10 factorial. So we're going to simplify this. So it's 100 factorial over 90 factorial times 10 factorial. Now I know that I'm not going to have enough room here to actually, you know, show and do the canceling out part, because I would have to have basically 10 numbers on top, and I was kind of running out of room with 6 there. So I know I'm not going to have enough room to write down and try to simplify it and reduce the fractions that way. So at this point, I'm going to use my calculator, but I have shown enough work that then at this point we can do the calculator and we know what's going on. So if you've got your, the 100C10 button, or, your NCR button, you can do that. Or if you don't have that button, what you would do on your calculator is you would do 100 factorial, which is going to be like a giant number. My calculator can't even do it. My calculator just gave me an overflow. So that one's too big for my calculator. I can't do that. I might be able to do it if I divide by my 90 factorial at the same time, and then you would also be dividing by 10 factorial. So if I do it all at once, nope, my calculator still can't do it. So I'm going to try my NCR button. And in that case, my calculator couldn't do it. So you do have to kind of know what your calculator can do. And if it can't do it, what your options are. So my calculator can only do it through the NCR button. I don't know what your calculators can do. This might be one where I would, if I had more room, I would kind of write it out and put all the numbers and cancel things out just so that my calculator can actually calculate it out. So I got 1.731030946 times 10 to the 13. So that's a lot of zeros. How many digits do I even see? 1, 2, 3, 4, 5, 6, 7, 8, 9. So there's probably 4 extra zeros on this number, assuming that there's not more digits that my calculator is not giving me. It's possible that there's more numbers past the 6 and my calculator just cannot show those numbers. So I'm actually curious, and I'm going to do this on Desmos and see what Desmos gives us and if there are more digits. So this is also mentioned in the announcement I sent out yesterday about different calculators that can do these sort of calculations, because when you get really big ones, you get lots of choices. So Desmos does more than graph. Under Math Tools, it also has a scientific calculator. And you can find these under the function button here, right here. So it gives us a parenthesis. You're going to basically put them in with commas. So you put in n first, and then you put in your r, and that gives you your number. So it actually rounded. It gave us less decimals than my other calculator did. my TI gave me 1 more decimal. It rounded the 4/6 at the end to a 5 here. So it gave us fewer decimals. So just something to be aware of, that when you've got big numbers like this, it's rounding. So you're not actually going to have the exact number here, because our calculators are just rounding. They can't display every single number. So we're actually getting an approximation of the number of combinations, just because our technology does not allow us, the technology that we're using right here does not allow us to give more than that. And I don't think, there's no option to actually like give the same number of decimals. There may be some like scientific programs that give you more decimals, or that might be able to give you every actual digit. Of course, if you try to do it by hand, it would take a long time, and you can do that. But just as a point to know here is that when your calculator is giving you something in scientific notation like this, assume that it is likely to be rounded and may not be the exact number. So what we would do here is we would just kind of use the approximation symbol, and then you would have your thing. And if we really want to write it with all of the zeros, let's see, I said there was going to be 4 zeros after all of these numbers. So you could tack on the appropriate number of zeros to get it out of scientific notation. And it's approximately that many possible combinations of committees. The number of choices will go down the more people you have in a committee. So if
I just, on my calculator, made it 15 instead of 10. And then the exponent, nope, actually went up. There are even more combinations. Oh, I have that backwards. That doesn't make any. You should be dividing by, nope, you're dividing by fewer. Yeah, so the fewer people you have on the committee, the fewer number of combinations you actually have. But so that's how you do this kind of problem. And, you know, just be aware that you will have some issues where your calculator will round, and so you don't have the exact value. Are there any questions? Okay. So example 2, this is the same situation. We've got 3 different questions here. So this is for a Powerball. The game is played by drawing 5 white balls out of a drum of 69. So they're numbered 1 through 69. And then you have 1 Powerball that's red out of a drum of 26. So those are numbered just 1 through 26. So we've got 2 kind of things going on here. The jackpot is won by matching all 5 white balls in any order, and then your red Powerball. So if you wanted to find the possible number of winning Powerball numbers, you actually have 2 calculations to do first. So first is to find the possible number of combinations of white balls. So how many different ways can we get 5 white balls? So, you know, how many ways might that happen? So that is, we've got 69 white balls. So the n is 69, and we're choosing 5 of them. So R is equal to 5. If they're numbered starting at 0, there would actually be 70 of them. 0 to 69, that's actually 70. But we've got 1 through 69, so there's 69 of them. So we've got 69, choose 5. So that's 69 factorial over 69 minus 5 factorial, also over 5 factorial. So this is 69 factorial over 64 factorial, 5 factorial. So I'm going to just use my calculator to calculate this out. So, and I encourage you to try to do that with your calculator so that you know how to use your calculator and you can get these numbers as well. So if you have a calculator and you're able to calculate it, feel free to put in the chat what your number is so we can verify that everybody's getting the same number, you know. When I do this, I get 1, 1, 2, 3, 8, 5. Oh. 3, 8, 5, 1, 3. So 11,238,513 ways to arrange 5 white balls when there's 69 numbers there. Order doesn't matter. Now we want to find the possible numbers of getting 1 red ball, the possible number of combinations. So there are 26 red balls, so that's n equals 26, and we're just choosing 1. So we have 26, choose 1, which is 26 factorial over 26 minus 1, not minus 5, minus 1 factorial times 1 factorial. And this actually is going to be the same as the number of permutations, because if you're only choosing 1 item, it doesn't matter whether it's ordered or unordered, you're going to get the same number because the order doesn't
makes sense in this situation when you have only one. So the number of ways to pick one is the same as whether it's a combination or a permutation. So you could use either formula in this case, but because we're doing combinations, I'm, choosing combination here. So this is 26 factorial over 5 factorial times 1 factorial. And this is actually just 26. 1 factorial is equal to 1, so you're just dividing by 1. And then the divide by 25 takes away 25. That leaves you with 26. So this makes sense. If you're only choosing one thing and you've got 26 to choose from, of course there's 26 different ways to do it. Like, you don't even really need to do the formula here, but you can see that the formula does get you to the correct answer if you just think about it mentally. That there are 26 ways to pick 26 numbers, if you're only taking one of them. So now we want to find the possible number of winning Powerball numbers. So if you're playing Powerball, how many choices are there of possible winning numbers? And that would be, kind of give you an idea of the odds, like, because you're picking one out of those number of choices that would be the winner. You can see how hard it would be to win Powerball. So Powerball numbers, you have to match the white and the red. So this is actually going back to the counting principle. So the counting principle is when you're multiplying your possibilities together to get a total number. When you've got different events and they're occurring at the same time, you're multiplying them together. So this is what we call a counting problem, basically. We're using the fundamental counting principle. So this is the possible combination of white times the possible combination of red. So possible white times possible red. So you're taking that 11 million number and you're multiplying it by 26. And making sure that you don't type the number in wrong. I have this written down on paper to make sure I get the same number. Okay, good. So we get a number 292,201,338. So that is how many possible combinations of numbers you can get for the Powerball. So if you were to do the Powerball, the probability of winning is 1 out of that many. So very, very, very small possible chance of winning if you're looking at probability, because you would have to match them, 1 out of that many choices. Are there any questions? Okay. Here's another example. An employer interviews 12 people for 4 openings at a company. 5 of the 12 people are women, and all 12 applicants are qualified. So we're assuming that all 12 could get the job. Now, for this type of problem, we're going to assume that they're all going for the same position, because if you're going for different positions, then the order might matter because you're picking different positions. But we're going to assume that the 4 openings are for the same type of job. So it doesn't matter who gets picked first. So, in how many ways can the employer fill the 4 positions when the selection is random? So if they're just randomly, they're all qualified and they're just totally randomly, picking people, you've got 12 people and you're choosing 4 because there's 4 positions. So your N is 12 and your R is 4. So we're doing 12 C4. So that's 12 factorial over 12 minus 4 factorial times 4 factorial. So 12 factorial over 8 factorial 4 factorial. So these numbers are small enough that you could just do each factorial part separately and then do your division, though it's still 12 factorial still got me a very large number. So I don't want to actually write that out and do that. But I could do like what I did before with the simplifying the fractions. So 12 factorial divided by 8 factorial will be 12 times 11 times 10 times 9, because then the rest of them are canceled out. And then I've got 4 times 3 times 2 times 1. So it's not too bad to kind of cancel out this way when the numbers are small. So 4 times 3 gives me 12, so I can cancel those out immediately. And then I can cancel 2 out of 10, and that leaves me to 5. Let me just stick it over there. And so you're basically just doing 11 times 9 times 5, or, you know, if I had the 5 above the 10, it'd be 11 times 5 times 9. But this gives us 495. So there are 495 ways that the employer can fill these 4 positions if they're just randomly picking from the 4 or the 12 people. So next, in how many ways can the employer fill the 4 positions when exactly 2 selections are women? So let's say they want to guarantee that they're picking 4 openings and they want to make sure that 2 of them are women, which makes the other 2 have to be men. So they're trying to, you know, be 50-50 here. So 2 have to be women, 2 have to be men. So now we're picking from different groups of people, because now we have to know, well, 5 of them are women. So we got 5 women, and that means 7 of them are men because they have to add up to 12. So now instead of picking out a 12, we're picking out a 5 and picking out a 7. So this is basically a counting problem where we're multiplying the number of ways we can pick 2 women by the number of ways we can pick 2 men, because once you've picked 2 women, the others have to be men in order to have exactly 2 that are women. So we're doing a counting problem here. Where we're picking 2 women times 2 men in order to get the 4 openings. So then to get 2 women, we've got 5 and we're choosing 2. And then that's 7 choosing 2 for the men. So we're picking from 2 different buckets now, and then you multiply those together. So that's 5 factorial over 5 minus 2 factorial. And if you want, you can just do that subtraction in your head, that's fine, and just do 3 factorial and 2 factorial. That is okay if you skip that step. And then 7 factorial over 5 factorial, 2 factorial. So 7 minus 2, it gives you 5. And so this, I'm going to just use my calculator to do this for me, just because I don't have a lot of space here. So I've got 5, choose 2, which is 10, and then 7, choose 2, is 21. And so we have 210 ways. So if the employer wants to make sure that they're doing 2 women, 2 men, so that they have exactly 2 women, there are 210 ways that they can fill those positions. So next one here, in how many ways can the employer fill the 4 positions when exactly 3 are men? So let's say they want to have 3 men, and then that leaves the 4th position to be a woman. And the key word exactly here is key, because exactly means that then the other ones have to be female. They have to be women. If it didn't say exactly, then it could, depending on the interpretation, you might think, well, maybe they just don't care what the 4th one is, and that includes men and women. And then that gets a little bit more complicated when you're looking at doing the math. But exactly 3 means, okay, 3 have to be men, so then we have to have 1 woman after that. So this is another counting problem, because we need to multiply these. So we've got 3 men, which means that we have 1 woman. So we're doing 7 choose 3 to choose 3 out of the 7 men, and then 5 choose 1 for the remaining woman. So this is going to be 7 factorial over 4 factorial, 3 factorial. So if you notice, the factorials in the denominator, those numbers add up to 7. And then multiplying by 5 factorial, and then the denominator is 4 factorial, 1 factorial. So you just stick this on the calculator. 7 choose 3 gives us 35. And then 5 choose 1 will give you 5. So 35 times 5, you get a 175. So there are 175 ways that the employer can fill those 4 positions if the employer specifically wants 3 of them to be men. Are there any questions? Okay, this is my last example here. So a shipment of 25 television sets contains 3 defective units. So that means that we've got 3 are defective. So out of the 25, that means 22 are going to be considered good. So they have to add up to 25 there. So in how many ways can a vending company purchase 4 of these units and receive all good units? So we want 4, so N or an R. So R is how many we're choosing. We're choosing 4. N is how many we're picking from. If we want all good units, then we're choosing 4 from the good pile. So that's 22 for our N. So, and the order that we're picking the TVs doesn't matter. So that's why this is a combination. So we've got 22, choose 4. So that's going to be 22 factorial. And then we've got 22 minus 4 and 4 factorial. And don't forget your factorial symbols. If you don't put that exclamation point there, it's incorrect, because that's what means factorial. So we've got 22 factorial over 18 factorial 4 factorial. So I'm just going to use my calculator at this point, because 22 factorial is big. If I wanted to, if I had more space, I'd probably just try to simplify it first. The 22 choose 4. That gives us 7,315. So that's how many ways they could get all good units if they're choosing 4 of them. In how many ways can a vending company purchase 4 of these units and receive 2 good units? So if 2 of them are good, that means 2 of them have to be defective because we want 4 total. So this is another counting problem where you have to multiply the number of good by the number of bad here to fill in the total 4. So counting problems can use both combinations and permutations, in this case, combinations. So we want 2 good, and then the other 2 have to be bad. So out of the good, we're 22 choosing 2, and then there are 3 bad that we're choosing 2 out of. So that's going to be 3C2. So we've got 22 factorial over 20 factorial 2 factorial, and then 3 factorial over 1 factorial 2 factorial. So I just did that subtraction there. And then I'm going to use my calculator to get these values. 22 choose 2 is 231. And then 3 choose 2 is 3. So 231 times 3, we get 693. So you can see that they're far more likely to get all good units than to get 2 good units, because there's more ways to get good units than only 2 good units, more ways to get all of them. Now this last one, in how many ways can a vending company purchase 4 of these units and receive at least 2 good units? So this one, we have to do slightly differently. At least 2 good units means that we have 2 good units. But at least could also mean that we've got 3 good units because we're picking 4 at least. So we could get 3 good units, or we could get all good units. So we've already calculated how many ways we can get 2 good units. That's 693. And we've already calculated how many we can get all good units. 7,315. So we need to find out how many ways we can get 3 good units. So 3 good units would be 3 good, 1 bad, because we need to have 4 total. So that's going to be 22 choose 3, and then 3 choose 1. So 22 factorial over 22 minus 3 is 19. So 19 factorial, 3 factorial times 3 factorial over 2 factorial, 1 factorial. So I'm going to, normally if I had much more space, I wouldn't be doing it in 2 different sides. I'd probably do them all in the same, kind of go vertically down or something like this. But I have the space that I gave myself. So we're going to do 22 choose 3. So that's 1540. And then 3 choose 1 will give us 1, but you can do the math, or give us 3. You can do the math to verify. And so to find how many ways you can get at least 2 good units is if you get exactly 2, exactly 3, or exactly 4. So that's these combinations. And so now we just need to do the math. So 693 plus 1540 times 3 plus 7,315. So you can do all of that kind of in your calculator at once. And we get 12,628. So that is the number of ways that you can get at least 2 good units. So you have to really pay attention to whether it wants exactly 2. And if it doesn't say the word exactly, assume that it's got the word exactly in there. And then at least means that you're going to be adding on that many, plus you may have more than that. So you have to consider each of these separately. There's no way to kind of do at least, I mean, the only way in this case, and this goes back to something that you'll learn with probability, is that if you found out how many ways you could get 0 or 1, you could subtract those from the total ways to just pick 25. But I don't know if that's going to be any easier than doing it this way, where you've got the number of 2 plus the number of 3 plus the number of 4. There are questions? Okay, so that is combinations. The key is you're doing problems where the order doesn't matter.